Research network, DAGAL, which is an EU-funded network. There's some little posters near the door. I invite you to take these home and put them on the notice board in your institutions. We just started hiring 8 PhD students. That's, at this stage, not very much of interest to you, unless 1 or 2 of you are master students. But it's of interest to us to hire the best students. So if you know good master students at your own institutions, point these out to them. There's very good opportunities to work within this team. And we also hire 2 postdocs, as you may have seen. 1 postdoc on numerical simulations of local galaxies to work with Liat and Asula in Marseille, but within this network, and another one on kinematics of local galaxies to work with myself and other people at the IAC. So I'd just like to point this out to you while you listen to John's talk. Keep in mind that if you think, oh, I'd like to possibly come here, apply for jobs, there are many opportunities. So I invite you to talk to us during this week or email us later and then apply if appropriate. So after that deviating introduction, here's John Beckman. John Beckman is Emeritus Research Professor at the Spanish Research Council, the IAC, and a professor at the IAC. He's been at the IAC for, I guess, about 25 years now, or 27 years. And he will summarize galaxy research at the IAC. So, welcome.
Right. Well, a few days. Well, first of all, I suppose
Yeah, that's it. Yeah, okay. Good. For example, this is a study of the Large Magellanic Cloud, fields of stars in the Large Magellanic Cloud. Using the color magnitude diagrams and some spectroscopy, they can look at the way the age and the metallicity of the population varies with position in the cloud in a very detailed way, in a way you can't do for more distant galaxies, where you have to rely on merged products of stars. So that's one active group. Another group has been working for many years on a near-infrared survey of the galactic plane. They used the 60-inch, otherwise known as a 1.5-meter, Carlos Sanchez infrared telescope at our observatory. And they have made a major contribution to our understanding of the structure of the Milky Way. This is because they could use this telescope for weeks on end, whereas you can't use a big telescope for more than 2 or 3 nights. At our institute, we have some small telescopes which have made some very interesting discoveries, not only in galaxies. One of the things that they measured was the fact that the stellar bar was with a different position angle and a different length, longer, than was the general view when they did this work. They published it. As usual, it was taken little notice of until the Glimpse survey with Spitzer Galaxy rediscovered it. But the people in that survey didn't know about the work that was done here. They published anyway, and eventually they actually didn't issue an apology, they issued an acknowledgement that this had been in the literature for about 10 years previously, and was actually a very detailed look at the long bar of the galaxy. That's why the stars and stripes they're ironically stuck at the end of the long bar there. The same group is now working on the EMIR Cool Infrared Spectrograph, which is going to be put on our 10.4-meter telescope, the GTC, which, as you probably have been told, is at the moment the largest optical infrared telescope anywhere. So, well, at least on this planet. We're not talking about exoplanets now. Okay, so there's another group working on understanding the formation of the central regions of disc galaxies, and this is very akin to the work that is being done by some of the people who've been speaking to you, some of your lecturers here. They work with a group at Padua Observatory, and they specialize in photometric decomposition of galaxies, intrinsic shapes of bulges, and then the properties of bars. Those are the people who work on it. They have developed their own algorithm to perform two-dimensional photometric decomposition. It can fit 4 different components: a bulge, a disk, different shaped bars, and nuclear components. And they have tested and used these in a series of articles. They also work on the intrinsic shape of bulges, and this is an analytically. It's been done analytically because Simoneau is an analytical theorist to try to use two-dimensional information about the shapes of bulges to infer the three-dimensional structure of bulges. Obviously, you have to make reasonable suppositions. And I must say that they are using suppositions about spheroidal shapes of bulges. And I have to also admit that I'm not going to talk about pseudo-bulges in this talk, even though there is work on pseudo-bulges going on in the IAC. So this is just a particular group doing a particular piece of work. And they have worked on quite a large number, and they've derived the axis ratios of these bulges. Then, looking at bars. Now, this is what I was sent by them. This is not much. Very little of this is my own stuff. so I take little responsibility for statements such as 45 degrees of disk galaxies are barred, because personally, from my own observational experience, I'm sure, and those of a number of people in this room, Johann himself, I know that a higher fraction of galaxies disk galaxies are barred. But anyway, this is what they obtained from their studies. So, properties of bars. Bars are good traces of disks. They suggest from this that no disks are present in coma-dwarf galaxies below a certain magnitude. And so they're looking at bars in this way as disk tracers for weak galaxies, because obviously the bars are often the most luminous components of disks, just because of the higher column densities. So this is a particular piece of work they're doing. Now I'll go on to a more major piece of work, which is the S4G Galaxy Survey. There's a group at the IAC led by Johann, which is linked to this very powerful US-based major study of nearby galaxy structure. We know that if you observe in the infrared, you get rid of some problems of measuring the stellar component of galaxies. Obviously, it's dust. If you observe into the infrared, you get rid of many of the problems of dust, not all of them. And so, when the Spitzer satellite ran out of its cryogenics and became Spitzer warm, well, warm I think is not sure the exact temperature, but it's minus 70 or something like that, then it's still useful to make good high signal-to-noise measurements of disk galaxies. It may not be good for everything. So this group, and a number of its members are here today, took the idea of using Spitzer and building up a big catalogue of very precisely and deeply measured images in the infrared, from which you can do the kind of work of disentangling the bulges, disks, bars, and then relate those to other kinds of observations. For example, you can do a kinematic follow-up. You can, if there's gas, which in many of the galaxies obviously there will be, you can do a kinematic follow-up using either 21 centimeter lines or H-alpha with the GAFAS instrument, which I'll describe a bit later. You can also do H-alpha, an optical imaging follow-up. And I'll be talking about Stripe 82, which is the deep follow-on of the Sloan. So there's the original Sloan and Stripe 82, which is a deeper stripe across the sky by the Sloan system. And that can also be linked to these S4G images. So there's a lot of science that is going on, all basic science, observational science of galaxies using as the basis this S4G infrared major catalogue. And this links to what Johann was saying before. There is a European network, DAGAO, and they are advertising for PhD students and 2 postdocs, and one of them at least, some of them will be linked to this work. A piece of work which has already been done from S4G is looking at thick disks. Thick disks in spiral galaxies are very interesting. I'm very simplistic in my thinking, and I have to be dragged towards things which are important very often because I don't like them, because they're too difficult. And, for example, dust. I spent many years hating dust because, of course, it gets in the way. And I still hate it, but now it's a slightly different, it's almost a love-hate relationship, because because I realized that you have to observe the dust anyway, and eventually you get to observe it, and anything you do in astrophysics you get to like, because you practice it, and you get intimate with it. So eventually I became quite used to working with the properties of dust in the plane of disk galaxies and so on. Thick disks is again something which, when I used to read about it with Jerry Gilmore and some other people, Rosie Wise, working on thick disks in the Milky Way, I thought this was just a menace. It was just another what do we really need? Another component? And haven't we got enough components in the galaxy? But it turned out that for both metallicity reasons and kinematic reasons, the thick disk is an isolated population in the galaxy, well defined, and it is another structure. And so, as we'll see a little bit later on, I'm going to be forced to do things with thick disks. But one of the ways of looking at thick disks, of course, is in the edge on galaxies. And of course, again, S4G provides very clean images of the stellar components of galaxies. So, Sebastian Comeron, who was jointly my student and Johan's student, and is now working with Johan on these problems of looking at the profiles, those up and down those stripes. See if I can move this thing. Yeah, up and down there. These are crosscuts at different radii, and you can distinguish the slopes, the slope near the plane. This is near the plane, and then further away from the plane, two components. And by looking at these, you can measure the scale length of the thick disk and the thin disk in an edge-on case. Edge-on case and face-on cases for galaxies are very often different. Give you different information, complementary information. So this is work which is going on, and they've recently published a very nice paper on this work. These are some of the details. One of the results that they get is that the thick disks are more massive than previously thought. They're not, I would say, ubiquitous, but they're very common. By comparing the observed light profiles to grids of models of coupled disks in equilibrium, this is a piece of theoretical work, the S4G group is big enough that it can include real observers and real theorists who actually talk to each other. And so they have managed to derive more importance for these thick disks. Now, another group working on the outer parts of galaxy disks. These are disk profiles. And because Pete van der Kraut is here today, I can say that Pete was the person that discovered, or at least brought out, the truncations in galaxy disks many years ago now, in fact before I even came here. And his work was based on edge-on disks, again, and he noticed that the images ended rather abruptly, and he analyzed this, and he coined the term disk truncations. And he also probed the different scenarios that these could bring these about. Nearly 20 years later, Michael Pollan, who was then in Germany working on his PhD thesis, made a detailed study of disks using CCD data. And he found an apparent contrast between edge-on disks, which seemed to cut off sharply, and face-on disks, which seemed to fade away. But he made a modeling exercise in which he took an edge-on disk and turned it face-on to see what the effect would be. And he found that really the two systems were really very similar. almost certainly the same, as you would expect. There's no real intrinsic physical reason why an edge on disk should be different from a face on disk. So he was able to reconcile these and determine that the truncations were there, but they were not so abrupt. They were just best described in terms of two exponential declines in the surface brightness. The inner brightness falling off in a certain way with an exponential like this, and the outer bit falling off like this, with actually a fairly sharp break between them. So, then two groups, both of them working in the IAC, made systematic studies of these light profiles. One of the things that had been thought when these truncations were discovered, when you discover something, you think that you've discovered something universal, and of course it's very nice if you have. But sometimes it turns out not to be quite the case, and it turned out that not all galaxy disks are truncated, at least not observationally truncated in the same way. And two groups, one of them led by, with Michael Pollan and Nacho Trujillo, Pollan then being at the IAC and Trujillo being away, and another group with Peter Owen and myself and Michael Pollan, made this set of systematic deep face-on measurements of galaxies where we found that there were three basic types. There were these truncated disks with their double exponential. There were, which by analogy with previous work by Freeman, we called type 2. Then there were disks which just had a single slope, one slope, and as far out as you could measure, you couldn't find any change, and we call those type 1. And then there were the third type, which we actually discovered again, although people had spotted them before, but we systematized them, where you have the inner slope, which is actually steeper than the outer slope, and we call those anti-truncations. And, well, we measured a lot of these things. There's a mixture of all these different types. Type 3s, interestingly enough, we found again came in two flavors. One flavor where, indeed, it went like this. You could find a break radius with an inner profile and outer profile. And the other where you had the inner profile, a single clean exponential, and the outer profile gradually fading away. And when we found this, we said that we thought that the clean breaks would referred to disc-like structures, so the inner and the outer parts are both discs, and the fading away part probably were galaxies where the halo was beginning to be detected. And we confirmed this because with the D types, the disky types, when you measured the isophotes, the isophotes of the inner disk and the outer disk lined up perfectly. That is to say, they had the same major axis and the same ellipticity. But when you measured the type S, where the fadeaways, then you found that the outer isophotes became more and more spherical. So indeed, that was our hypothesis. And we'll see that this is very probably the case. We'll see some work by Judith Bakos, which I'll talk about a little bit later on. So these are the different type 3 profiles. And this, we had a complete classification scheme. Now, we know that in science, one of the first steps towards understanding is classifying. It is only a first step. You can't think that you understand something when you've classified it. But of course, classification helps because if you find consistent features, then you know that you have to have a consistent physical explanation for those features. So we found different types of profiles. The type 2s, we found some which seemed to be related to the bars and to the ring structure associated with the bars. In other words, that these were caused by resonance. In others, we didn't find that. And as I said, with the type 3s, some we found that were disky and some we found that were more spheroidal. And we also found that there's a variation with Hubble type in the proportions of these different profiles. So that type 3s, there are, the truncations, the type 2s, dominate in later type galaxies. So if you're doing a project in the beginning with only late type galaxies, late type disks, you might well find that there are very few that are not truncated. But if you go to the earlier types, you find indeed that the smooth ones, the type 1, and the antitruncated type 3 actually dominate over the type 2s. So these are, these are all local galaxies, very well resolved and very carefully measured. The problems practical problems of doing this are basically, how do you measure the sky background? Because if you make a mistake with the sky background, the outer parts of the galaxy are hopelessly badly measured. And how do you get rid of the stars in the field and mask them? There's technical things, as with in every case. There's detailed technical work which goes into this stuff, but it isn't particularly difficult. The major fraction of type 3 antitruncated profiles tend to prefer unbarred galaxies, and there are two scenarios which have been proposed for them. Now, I'll be talking a bit later about models which can explain truncations. And indeed, quite a lot of interesting theoretical works have been done to explain truncations, and it's very illustrative work. But this was done in a way before, or not taking into account that what you really need to explain is the absence of truncations in a large fraction of galaxies. So quite a bit remains to be done on this. There is a model in development by Inma Martinez, who was here, who's actually worked with Isaac Schlossman and with Leanna Athanasoul, and is now working with Ortwin Gerhard, and came from the IAC and has worked with the IAC, where she just takes a dynamical interaction of a disk, a bar, and a live dark matter halo, and if you get the parameters right and have a weak bar, then she can in fact produce an antitruncation. But there's another recipe for antitruncations which I think is probably more general and at least as interesting, and that is the arrival of a small gas-fairly rich dwarf galaxy and its absorption into the main disk, because when we measure the properties of these antitruncations, we find the following. We find that the ratio between the scale lengths of the inner part and the outer part doesn't vary very much in the population of these things. It does vary, but it varies by a factor of perhaps 2, occasionally a little bit more maybe, but not much. Whereas the place where this transition takes place, that is to say the surface brightness at which it takes place, or the radial distance from the center, varies a lot more. And it seems to me that all you need to do to produce these effects, and there are some other effects, is to take a gas-rich dwarf and let it be absorbed let it be merged into the galaxy, whereupon the stars will go to form the thick disk, and the gas will settle to the plane and eventually contribute to the thin disk. And eventually you'll get one of these antitruncated galaxies, and this is a fairly common procedure. And it would explain why many galaxies, but not all, do have these antitruncations. In a paper which we're just writing at the moment, or in fact we finished it, and it's well, I say almost impressed. It's just about to be sent off, in fact. So I'm being optimistic, but still, it's fairly basic. There are statistics on early type galaxies in the Virgo cluster and in the field, and they show that there are no. These are early types. They're not late type galaxies. They're S0s. But they show that there are no type 2 galaxies in the Virgo sample, but more type 1s and type 3s. And this is clearly a clue about the various formation mechanisms. So, for example, we know that in clusters there's harassment and the starvation of gas and processes which can affect the formation of structure. And this is one of the ways in which one can obtain the observational basis to make the models about what's going on. Then, samples of galaxies at intermediate redshift. In his PhD thesis work at the IAC, Romano Tolini took samples of galaxies in 3 redshift bins from the Goods survey. So this is typical modern HST archive work, and he measured. He looked at truncations in these, and he found that he could go down to 26 magnitude per square arc second, which is quite decent. The profiles are reliable, both from Goods and from the those few galaxies that were also in the ultra-deep field didn't show significant differences. So that was work. And what he showed was that the break radius was small. That is to say, the radius at which this change takes place in the profile was smaller, was shorter, nearer the galactic center at a redshift of 1 than today, and in fact has developed, as you can see from the epigraph, almost linearly. If you plot it in bins of constant mass, then the trend is smaller numerically, but it's still a very clear trend. So this is, again, an interesting look at development processes in disks. Why has this happened? Well, these are some more details, including some of his own sketches. These are color, and then also color profiles of the galaxies in the same sample. And this comes from Tolini, Trujillo, and Beckman, 2008. The bands were chosen to approximate to the colors in the rest frame band. So obviously, we had to use the best colors we could, the nearest we could. And we find, looking at the type 2s now, the truncated ones, where we found clear evidence of something. The evidence is that the colors at the break radius are bluest. That is to say, the colors are redder near the middle of the disk, become bluest at the break radius, and then get redder again as you go further out into the truncated part. The type 2s and type 3s type 1s and type 3s are a little bit more difficult to work with in this case. But this stuff was slightly changed by Judith Bacos working with Nacho Trujillo, because they changed the color into mass. They actually were able to use a thing with mass. They found a similar result. Everything is similar, and that is to say, yes, it is still the bluest part at the break, near the break radius, but the actual truncation was smoothed out if you do it in mass. If you do it in light, there's this clear, sharp break. If you do it in mass, the break is less. And they went as far as to say there wasn't a break and that it was all but that is not so. I mean, that was again, it's the pleasure of finding something new. You think that you've got an answer, and it's not quite. And the models for this, there are models which work quite well by Victor de Batista and Rob Roskar, where they use outward migration of stars coupled with incoming gas to keep the bluest parts of the disk at the break. Basically what happens is that the disk is growing all the time as mass is being accreted onto the galaxy, as gas is being accreted onto the galaxy, and also growing because some part of the stellar population is diffusing outwards, impelled by transient asymmetries, which are basically probably the arms, really. And they can manage to keep the bluest part of the disk at the break radius, and their models are reasonably good. They're not the only models, but they are. At least it shows that a rational model incorporating the kinds of processes which should occur can account for much of the data. And finally, while I'm talking about these profiles, deep surface brightness profiles of lake-type galaxies, and this is using this deep stripe 82, it enables much deep. These are comparing the original Sloan with the stripe 82 images, and you can see that they're much deeper, and they reveal more structure, and they go further out. And so these are this is the profile of one particular galaxy, which the observations are the observational evidence is up here. Well, it's up on the left, and the analysed into components here on the right. And what they are saying is that they go right down to below 28th magnitude per square arc second. So it's very deep data. And well, even down to 29th, yes? And pardon? Go down to 30. Okay, sorry, even down to 30. Okay, well, and yes, that's true, they go down to 30. And so they are detecting the halo again. It's the same thing. They see where the disk stops contributing as much as the halo, and this obviously is very, very powerful, because they can then look at the colours of the stars in the halo. You forgive me in all of these things if I'm shortening to almost nothing what you actually did. And they find these colours are so red that you can't fit them with a conventional IMF under almost any circumstance, and that you have to have far more low-mass stars in the halo than can be fitted by a conventional IMF, and that's a very interesting result. That's work to be published. And then work about how massive galaxies have evolved over cosmic time. So we're talking here about the most massive galaxies, greater than 10 to the 11th solar masses in stars, and most of them are early type. And the populations are, in any case, old and metal-rich, even when you observe these galaxies already at z equals 1 or 2, which means they must have formed very early. So they're very compact. Their effective radius is only 1.5 kiloparsecs at z equals 2, and they have much denser stellar structure than the same types of galaxies here, local galaxies. So this is actually, there's a lot more in this research than I can possibly convey in these few slides. So first of all, they get a result where they have size evolution of massive spheroids. That is to say, these massive spheroidal systems are very compact at z equals 2 and so, and things of similar mass are much bigger now, or things with the same radius are much less massive. And they try to see why this is. And basically, there are two different ideas which they're testing. Well, I won't. Yeah, okay. Look at where it says at the bottom, models for this spheroid size evolution. One is what they say puffing up. what is this? This is where you have an AGN in the middle of this thing, and we know that there are powerful AGN, active galactic nuclei in the middle of these spheroidal systems, asteroidal systems. This removes the gas from the galaxies and weakens the gravitational field to the point where they get puffed up. That's one possibility. The stars expand, the spheroid expands. Then major dry mergers, that is to say, spheroids merging with spheroids. And the third is minor merging, where the massive original thing accumulates smaller galaxies over a long period of time. And without... so the puffing up process is very fast, and there's no stellar mass increase, and there's a strong decrease in the velocity dispersion, so there are predictions from these. And the accretion predicts something different. It predicts that there is a mass increase, the size increase is continuous, not rapid, and there is a mild, slow decrease in the velocity dispersion. And eventually, there's what the observations tell us. They tell us, first of all, there's no mean size difference between young and old spheroids at any given value of Z. And this result tells against the puffing up model. Steady progressive formation of the outer galaxy envelopes, which is again against the puffing up model. And the velocity dispersion evolution is progressive and slow, and this again tells in favor of the accumulating minor merger model. So, and also they look at the star formation history, which can be done conventionally with ordinary spectra and colors, or now they can use Herschel results in the infrared. The results they're getting for these star formation histories suggest that the puffing up models don't work. So, the other thing is that elliptical galaxies or spheroids are dominant only since Z equals 1.5 approximately. So I'll have to go quickly because there's a lot to say. But the summary is this, that the most favored picture is that the bulk, the core of these massive galaxies is formed very early on. Z is 4 to 5. And then in a single dissipative event. And then onto this condense or four minor satellites which create the outer envelopes, which are in any case more diffuse. So that is their present result. Now I'm going to talk about work on with the GAFAS Fabry-Perot spectrometer. I wasn't going to talk about this, but the person in charge of GAFAS insisted that I did it, so I have to do it. Well, in fact, I'm in charge of GAFAS. So it's a Fabry-Perot spectrometer. Here are the technical things. Actually, it's a very neat, compact instrument. And what it does is optical radio astronomy. Because what we are doing when we look at galaxies with it, we are making a map of a galaxy in a single emission line with high resolution spatially and spectrally. So we get the same as a 21 centimeter map in terms of spectral, well, better spatial resolution. We're usually seeing limited at about 1 arcsecond or better, and spectral resolution or velocity resolution of order 10 kilometers per second. It depends. The other thing is that we can make a map of a galaxy going down to covering at least the whole of the disk out to where the spiral arms can't be really seen anymore in a few hours. 3 hours, we say, but perhaps really about 5 hours. So, and again, it's much quicker than a VLA or Westerbork or other equivalent map of the same object, and it gives you very similar information. That's the upside. The downside on this is that the H alpha is it's patchier. It's clearly patchier. If we wanted to get it as continuous, we would have to go a lot deeper, and then we would be looking at nights of observation per object. And this we could do, but we don't tend to do it at the moment. So, and here is a quick kind of look at the kind of information you can get. You take this, it's a scanning system in which you get what's called a data cube. Again, this is familiar to radio astronomers, where the cube can be divided into planes, and each plane is a map of the galaxy in a certain velocity range. You can combine these to produce a single map of the emission of the galaxy in H-alpha, just like the column density in H1. This is the surface brightness in H-alpha. And you can then also combine them to produce a velocity map, complete radial velocity map, or a velocity dispersion map, and then you can do the usual things that radio astronomers do. That is to say, make a map of the non-circular velocities of the system, the velocities which depart from the stable circular velocities. And this is a case of something interesting that we recently did, an application of GAFAS to a pair of interacting galaxies. It's a well-known system, ARC-271, and what you do is you have maps. This is where's the thing? Here we are. The optical image, and here is the H-alpha map, just the intensity, and these are velocity maps here. You can see the typical rotation pattern. This, however, this gas here is not the map of this galaxy. It's a map of H1, which has the velocities of this galaxy. And let me switch quickly. When we look at the upper galaxy, we find two different velocity maps. One of them pertaining to the galaxy, and the other pertaining to the other galaxy. And the reason is that what we're finding is in falling gas from the lower galaxy, which has passed behind the upper galaxy a few million years ago, and left behind it its infalling gas, which we can tag by velocities. We can measure a sort of rotation curve of the lower galaxy, and in that curve has an anomalous thing here, funny thing here, and then all this stuff here, and we can work out that this is infalling gas. That the middle bit, the middle bit is actually the gaseous wind. Where is it? The gaseous wind. This is over the nucleus of the upper galaxy. This is the wind flowing out of the upper galaxy due to the very high star formation rates in the upper galaxy. And this is actually gas from this galaxy falling onto the upper galaxy. We can work out, and it's being ionized by escaping Lyman photons from the upper galaxy. You can work out the infall rate of gas. You can work out a structure, a three-dimensional pattern stylized in these images at the bottom, where you can see a galaxy plane with a kind of cushion-looking thing of gas being ionized and falling onto it from behind. And so we can work out the actual gas accretion rate, and it turns out to be about 10 solar masses per year of gas, and then you can work out how much extra star formation you should be getting. Well, this is something you can do if you have high spectral resolution and high spatial resolution. And then another thing is to find resonance structure in galaxies. James Binney is working his way to explain the basis of resonance structure, and we know that resonance structure is important. That the density wave theory in its various forms, more or less sophisticated, implies a co-rotation radius where the the pattern of the density wave and the actual material are rotating at the same angular speed, and then other resonances, couple resonances, and one of the ways in which you can find these resonances by using the famous Tremaine-Weinberg method, but really to do that you need a velocity map in stars and a density map in stars, and you can combine those to give you the to work out where the co-rotation radius is. It's very interesting to work out co-rotation radius because models of galaxies forming in dark matter halos and being dynamically slowed down, braked by dynamical friction with the halo, predict that these pattern speeds should be slow, and predict that the pattern speed relates directly to the co-rotation radius. So if you measure the co-rotation radius, you can derive the pattern speed and see if it's slow or fast. And so this is one of the motivations. There are many other motivations for measuring these things. What we find is that we can do a rather simplistic trick with the kind of data we have, because it's so well resolved spatially and spectrally. What we can do is we measure the velocity field of a galaxy, as you saw before. That is to say, the typical spider diagram of the radio astronomer's velocity field, and then we can measure the rotation curve. We subtract the rotation curve. We rotate that curve through 180 degrees, and we subtract it from the velocities, and we get a map of the non-circular velocities in the galaxy. And these non-circular velocities are related, in some cases, at any rate, to the resonance structure. And what you should find is that, for example, when you go through co-rotation, motions in the arms, as the so-called streaming motions, change their phase by 180 degrees. And we can detect this by zero velocities in this map of the residual velocities. So we make a plot of where are the zeros. You reject zeros where the change of velocity is very small, because that could just be noise. So you throw away a large number of these zeros because they're just noise. But all those which satisfy a condition so they're not noise, you incorporate into these plots. And you just plot against the number of these zeros against radius, and you get this map of sharp peaks. And these sharp peaks are the resonances. Now, you have the difficulty of identifying which are co-rotation, but you can do that usually structurally. Are they related to the bar? Or, if you're desperate, you can say which is the strongest of these peaks and say that's co-rotation. There is still some ambiguity in this. Nevertheless, this is a paper we've just published, but we've done this now for over 100 galaxies, and we find this map of very sharp peaks, and we can cleanly identify the co-rotations in a large number of galaxies this way. So it's another example of what you can do with this kind of data. And finally, I'll talk about electron densities in H2 regions across the whole disk of a galaxy. And this is clearly and unashamedly my work, and that's why I'm going to talk about it, not for any other reason. Well, there is another reason, because I happen to have this piece of material prepared because I gave a lecture last week at a conference about it. So that's another good reason to talk about it now. So the 10.4 meter Grand Tecan GTC is now operational. As I said at the beginning, it is, at the present time, the largest, happens to be by a few centimeters, the largest diameter optical infrared telescope operational in the world. Obviously, it won't remain that way. And it has two instruments, one of which is really working now well. It wasn't, but it is. And one of them is called Osiris, and another instrument which is called CanaryCam, which is an infrared camera, a middle infrared camera. Now, one of the nice aspects of this OSIRIS instrument is that it has a tunable filter. It's a Fabry-Perot style, but not a scanning Fabry-Perot for higher velocity resolution, but just a narrowband filter that you can tune. And so you can make measurements of emission lines across whole galaxies. And so that's what this is about. This is a galaxy, a very well-known local galaxy, suitable for all kinds. It's a very accommodating galaxy because it is at 45-degree inclination. Therefore, you can make measurements of its morphology and its kinematics at the same time. So it's a very kind galaxy in that respect. This is the pattern for use to make these measurements. The measurements are going to be, or are, of the two lines of the sulfur-2 emission doublet and at 6717 and 6731 angstroms. The point, why did we make the measurements? What we wanted to do, these measurements allow you to measure electron densities directly in situ in H2 regions. And so what we did was to use this technique. Now, this filter, you can vary its central wavelength, and you can vary it to a limited degree its half width. So we tuned it. We had to scan the whole galaxy and get the two lines and be able to deblend them. We needed 19 exposures, and the whole thing took about a couple of hours, approximately a couple of hours, including the sky data. There we are. The final filter that you get when is built up of these 19 single filters. This is the final passband, and these are the two doublet lines. Well, I won't go into the techniques of how you scale the things and how you get rid of the sky and how you get rid of the continuum. Eventually, you get a spectrum. It's of course, this is not a spectrograph. It's filter. It's a tunable filter. So it has a lowish resolution, but luckily our lines are sufficiently separated that you can separate them with these filters, and you can make what's called a pseudo-spectrum. And again, without going into details, you can measure these, the line ratios across the whole galaxy, the whole of the galaxy. We've detected nearly 850 H2 regions in this object, in these lines. At the moment, we've derived nearly 400 values of the electron density covering the whole galaxy. We can do much better than this in certain ways. For example, in the biggest regions, we will be able to measure how this ratio varies from center to limb of the regions as well. But anyway, this is what we've done so far. We only had the data for a few weeks, in fact. And just pay attention to this graph here, which is the electron density measured by this method, at least to a first approximation, because we have still work to do on it, from near the center to near the edge, in radius of the disk. And you can see that the values here are 350 per cubic centimeter, and here they're down to 200. So we eventually will have a map of the electron density over the face of the galaxy. Clearly, the decline is obvious, and we'll be able to quantify it further. But those are in situ electron densities. Those electron densities are, remember, they're in a range 300, 200, and so on. Those densities pertain to the clumps of higher density gas which give rise to this emission. And when you measure the electron density of an H2 region in a different way, you get very different values. You can measure the electron density of the mean electron density of an H2 region by measuring its total flux in H alpha and its radius. And you can quite simply use these two values to give you a mean electron density. You have to make, in both cases, you have to make some supposition about the temperature, but it doesn't vary a lot with temperature in either case. And then you get values which are about 10, or between 10 and 1, and instead of being a few hundred. Now, this is very well known in all the textbooks, it's a very well-known thing. It's a filling factor because you have an H2 region is a very inhomogeneous thing. It has dense clumps at a lower temperature and diffuse matter at a warmer temperature in some sort of equilibrium. And so the mean value is over the whole region, and the in situ value is in the clumps. So what we've measured here are the mean values, and we have two properties of these things. These graphs are for two different galaxies. One is a big galaxy, M51, and the other is a dwarf galaxy. And we can see that in both of them, the actual physical relationship between the number of electrons per cubic centimeter and the radius of the region, now these R's are the radius of the region, there's a simple relationship that goes as the radius to the minus 1/2. This is based on HST data, and nobody has got this clean relationship before. And there's another relationship we can get, which is the relationship between the electron density and the galactocentric radius of the H2 regions, taking into account the scatter due to the different sizes of regions. So you can separate, we have so many regions, we can separate the two variables. And what you have here is that there is an exponential decline in this mean electron density, and the scale length of this exponential decline is the same as the scale length of the 21 centimeter emission from this galaxy. And it's in fact the same in both galaxies. But whereas in M51, the big galaxy, the H1 has a longer scale length on the stars, but it isn't many times longer. It may be twice or so. In the other galaxy, the H1 scale length is perhaps 10 times. The stars are much more compressed. There's a huge cloud of H1. So, what does this mean? It means that H2 regions are in pressure equilibrium in the plane of these galaxies. And this is again something which has not been considered correct by the experts in H2 regions. So, this is what you can do with galaxy-wide semi-statistical evidence about these. Really, we're not talking about galaxies, we're talking about H2 regions. Nevertheless, you can learn from looking at whole galaxies at a time, you can learn something very interesting about how H2 regions behave and how massive stars interact with their surroundings. And so on and so on. So I've given you a not representative overview of what work is being done at the IAC. There's far more work than that. There are a number of people, for example, working with Herschel on the Herschel program. There are a number of groups working with high Z clusters, which I haven't talked much about, a little bit, but not much, and many things besides. But I've given you a taste of what is being done, the scope of things that are being done at the IAC, which covers a major part of modern galaxy research. Right. Thank you. If there are no questions or comments, I can take this. Oh, there's okay, Pete, good. Yes, Pete. Better have a microphone, yeah.
A number of things, John. In the first place, let me say a few things about this last stuff, about the H2 regions. I remember for work we did in the 70s in Westerbork on the thermal fluxes from the H2 regions. There was quite significant amounts of absorption that you don't see in the Balmer decrement, particularly because the things are optically thick. Mm-hmm. So what's the effect of absorption on them? Have you used actually thermal radio fluxes to compare these electron densities to how they fit to those observations?
Well, the dust corrected, because in the case of H alpha it's dust correction, it isn't gas absorption. So it's, the fraction of dust correction is fairly low. In the most compact H2 regions, it would not be so low. But as far as the in situ stuff is concerned, it's clear that it doesn't matter very much, because these are two lines separated by a relatively modest wavelength range. So it's the rate and it's the line ratio. So there are two different things. The mean values probably do need some correction, and the in situ values, I think, are pretty good.
Okay. The other thing about transients, there are a number of things that I think are interesting. In the first place, I'm not fully convinced yet that we reconcile the view in phase-on and edge-on from each other. In particular, that we haven't been able yet to, I think, to turn a phase-on galaxy edge-on. Stefan Peters, who was here sitting here, has done his master thesis on that. Maybe you say things about it. But let me say this first. The type 1s that you have, the things that continue indefinitely, seem to me, but I haven't done the full statistics. I wonder maybe that you have done that. Seem to me the ones that have abnormally short scale length. Of course, it's known for bigger samples that there is a correlation between the rotation velocity and the scale length. There is a correlation between the rotation velocity and the truncation radius. Now, these correlations by themselves, of course, don't say much. Some simply say that when there's more galaxy, there's more galaxy. But there is scatter in them. And it seems that certainly that particular case of NGC 300 that Ken Freeman and Josh Blash Hawthorne showed is a case in which the scale length, although it goes out to 10 scale length, but it has a very, very abnormal scale length and might still within the rotation velocity have...
I agree with that, and obviously your point's completely well taken. There is a thing, though. What I think the interesting thing about that and about some other measurements of type 1s in nearby objects is that they are being measured using star counts rather than using surface brightness. And that, I think, is significant, whether or not what you say is correct. And I think it may well be correct, but the point about those galaxies is that they were measured in a different way, and a way which is not so easy to fool, I think, by flares or by dust absorption or what you will. So I would say I would attribute more importance to that aspect of those measurements than to the actual measurement itself, in a way. And I also take your point well. I think you're right that it may well not be so easy just to turn an edge-on into a face-on. I keep to my belief that I think stellar flaring has got something to do with it. But you wouldn't see that in a face-on, but you would certainly see it in an edge-on.
Yes, well, it's on the... it could be measured in principle, but it's difficult. The other thing is that when I look at the Poland et al. Sample, just looking at the pictures of the Sloan survey, my impression was that the ones with the upturn, the type 3, always were distorted, seemed to have outer ridge distortions, which fits a bit with what you said of infall of satellites. Is that a thing that... It
could be so, but as I am not responsible for that, I won't reply directly. But the other sample, the Irwin et al. Samples, don't suffer from that. There are many galaxies which are not Sloan galaxies in there, and they don't. So I can defend the sample that we published more easily than I can talk about the other sample.
And that doesn't have these. No. The data type 3s don't look like that.
Oh, it doesn't have. No, it has type 3s, but they are
normal.
Well measured normal type 3s.
Okay. Yeah. Well, the other thing I like to mention is the stuff that Stefan Peters has done. He's done two things actually. And I'll just show these done, and then maybe you should tell himself what the results are. The one thing he tried to do is to check on the Poland et al. Sloan survey surface photometry by not fitting ellipses to the isophos and get the radio profiles from that, but rather use the Vauquelin profiles, which are a completely different thing. And also he tried, to collapse them on the major axis to see what they look like edge on. So. And I did that for his master thesis, so I'd like to invite my student.
Okay.
I'm
That's
on
good.
this.
Yeah. Okay.
To say a few things about it.
Right. Thanks. Okay. Before I'll take the next question, but I think Judith Bakos needs to say something because she's been looking at some very deep exposures and going out further than we did.
Yeah, I would like to make just a comment on this reconciliation problem. So one problem is the signal to noise, and what we found on our galaxies, now that we integrate in a large aperture and everything, that the halo starts to dominate at about 5/4 this K length. So if truncations are at the same distance, using phase-on projections, what we start to see is the halo, basically. So you cannot reconcile this problem with phase-on galaxies. In case of edge-on disks, though, you don't integrate the halo into your profile, basically. And that's why you can't see the halo, for example, in phase-on projections. And of course, because you have lower number of pixels or so. Yeah, this is the comment.
Okay. Thanks. Yes, right. Another question.
No, I'm Stefan Peters. I'll
okay. Okay.
It's working.
Well, I don't want to cut you off. I mean, how are we for time? Is this all right? Carry on then. Okay. Carry on.
Well, the major two things we found was that first, the original technique, which I just completely forgot the name about, actually matches what the the elliptical fitting does. So there was an interesting find that it seems to be really unimportant if you're actually fitting the ellipses or just assuming that it's a centrally distributed function.
Okay, that's an important point, an interesting point. I don't want to question it, but I might question it. But anyway, carry on.
Well, I can show you after this.
Yes.
The second find I had was that I think that the type 2 truncations and the breaks are, first off, a really confusing naming scheme. I think we should just call that the truncations are not really what I think you claimed in your presentation a lot of things called truncation. I think those should stick to the type 2s, and I don't think they're truncations quite here.
Okay, well, actually, historically, we call them truncations to be kind to truncations, rather than for any other reason. Not because really we didn't want to reject the idea of truncations. But in fact, we normally call them type 2. We just call them type 1, type 2, and type 3.
No, exactly, I agree about that. But I'm just saying that I think the type 2s are actually something different compared to truncation.
Well, there's more than one type of type 2.
Exactly, and the major find I had in my master thesis was that it appears that if you project the face-on galaxy onto a single axis, that's basically pretending you're an edge-on galaxy except for dust attenuation. That it seems to be that the truncation-like features appear if you're just simply projecting along the line of along a spiral arm. So there's nothing else going on except that there's some twist in the spiral arm.
Okay.
So we had that as an interesting find.
Okay, thanks. Good. Thanks a lot. Right. Well, we've got into some details there. Okay, yes, Jacqueline.
I was struck by your picture of the two galaxies where you claim that the gas is falling in from behind. So I have two questions about that. The morphology of the infalling gas looks exactly like the morphology of the galaxy in front of it.
Yes, it does.
And so I was wondering, that must be because it's being photoionized?
Yes.
So then it
but not only that, there's another reason. The reason is, what I didn't explain this because time. We find that when you look at the spectra, where the emission from the upper galaxy is strong, the emission from the anomalous feature is weak, and vice versa. In other words, the anomalous emission is coming from the interarm zones. There's a little bit at the edge of the arm, and also off the edge of the disk. And why is that? That is because the stuff is falling from behind. So, and that's why you have a pseudo... It looks like... When we first saw it, we thought, how the hell... Pardon me. Does this gas have the shape of the galaxy in front of it? And it's for those two reasons. One is that it's being photoionized by the galaxy in front of it. And second is because it's behind, so it has a kind of... it's a kind of anti-image of the galaxy in front, because you see it through the galaxy in front.
Okay, so but then it must be part of a larger structure, right?
Well, it's not exactly, it's a structure, but it's a diffuse structure, because you have the kinematics of the galaxy going behind. The galaxy that's gone behind has to be at a certain orientation to the galaxy in front, so that as it rotates, its gas is the gas nearer the other one is progressively stripped off and falls piecemeal onto the other one.
Yeah, so I was wondering, could you see that in H1?
The resolution, our angular resolution, is much higher than I think is easy to get in H1. You might be able to see it, but you might be able to see it in H1. I wouldn't say you couldn't see it in H1. Let me say another thing. It would be worth a VLA map.
A question about the tunable filter data. I mean, I'm very glad to see that Gantakan is now finally being able to produce data of this kind. But in principle, you can do all this with the Fabry Perot. So could you comment on the improvements that on these data as compared to something you could have done with GAFAs? That's
something.
The first question.
Well, no, you can't easily. No, well, you can't really. Not exactly the same way. This is a broadband tunable filter. GAFAs is a narrow, very, very, very narrowband tunable filter with a very short wavelength range. However, so this broadband tunable filter has various aspects. One is that it has a much bigger wavelength coverage. I mean, it can be tuned over a very wide range of wavelengths, and it's relatively easy to get the full 8 arc-minute field if you handle the data right. GAFAs has a less than 4 arc-minute field. Of course, it isn't on a 10-meter telescope. But to follow from this point, we have every intention of putting a high resolution Fabry Perot on Grantacan, actually inserting it into the other instrument. There's a group of us working on that now, led by the Mexicans, because, as you know, these are collaborative projects between Florida, Mexico, and the IAC. Optically, and so we're involved in putting that onto the inside Osiris, so we'll be able to have both capabilities.
Okay, so if you would make a velocity field of the galaxy you showed right now, would it be comparable to a GAFA's velocity field?
Yeah, if we made a velocity field of it.
Velocity field.
Yes, if we can't do it because we have such poor resolution. But we will try. I mean, we'll make a crude velocity field. So we can do that, but it's very crude.
It's time for coffee. Thank you again, John, for your talk.